The purpose of this video is to show how to do the example, which is one line of the data table of the Throw Something Lab. I definitely do want to clarify that the expectation is before you're doing this, you've already completed another assignment that's connected to two-dimensional motion, or at least you have good understanding of two-dimensional motion, because this is designed to not necessarily introduce it, but to reinforce and to practice some calculations relating to two-dimensional motion. So in an effort, I have a picture here of me when I threw something, and I also have it on video here. This is the same action happening. I'm going to walk through the example of what happened here, and I would point out that this ball, this is the tennis ball up here. Hopefully you can see that. And I threw it from right here, so its path followed a fairly a curve as it came down, and it came down over here. This would be sort of like the path it would have taken. And I'll refer back to this picture a couple times as we go along. But the first thing this thing tells you to do is basically you're supposed to come up with a prediction of how fast you can throw anything and in miles per hour. And you'll just figure out what you want to throw. Of course, I threw a tennis ball. Those are great, but I'm not necessarily, you should ask me if it's something strange, but for the most part, we just throw something in a safe manner, in a safe way. And what you need to get when you throw it, this is what this first line tells you, is you essentially need to get a distance and a time. And so for me, when I threw my tennis ball here, I was able to measure in this distance along here. We show here from where it struck the table to where it left the table. That distance was 9 feet. And in your instructions, it tells you there that if you end up getting in something in feet, just multiply it times 3.28 to convert it to meters. That's actually wrong. That should say divide by, okay? So we'll divide by 3.28. And we're going to find that, in fact, our distance was 2.74 meters. Now, as we're filling this out, that's actually going to be, we're going to start filling out this data table. You're going to do a data table with this example, and then you're going to do you're going to do a line with this example, then you're going to do a line with your own data. So right now what we would have is Mr. Easley with the tennis ball, and our horizontal distance we just found to be 2.74 meters. You do not have to write meters since it's listed in the heading. If a column has a heading on it with units, you don't have to write the units there. Now we got to find time that was in the air. And there's a couple ways you can find time. You can use a stopwatch when it goes through there, you know, start and stop. Or the more accurate way, as you know, is to use the edit mode. I'm in edit of my camera here. It's maybe hard to see, but if I hit edit, then you can actually drag it back and forth, and it's kind of hard to see on here. Move this up. But you can see right here, it gives decimal seconds. So you can get a timestamp of when it hit the ground. You can see it hitting the table right there, 363. And then if you drag it all the way back to where it's starting, you can get a timestamp of when it starts, when it leaves my hand, kind of right there. The timestamp is something like 253. This is a timestamp you can get from there, 256, 253. I wrote down earlier 256, or I'm going to call it, just for the sake of this, the time that took, I'm going to call it 0.8 seconds. And so that will go in your data table here, time 0.8 seconds. Horizontal velocity, so as we're going along here, we just actually did step 1. Now we're going to do step 2. And it says to use this equation to find the horizontal velocity. I'm going to do this on my own piece of paper so I can write bigger. And it's worth noting that what we're actually trying to do here is this first thing. Remember, the ball launched at an angle with a set velocity. We call that v. But remember, we can always think of this velocity in terms of the x component and the y component. And I just fixed that graphically. It should roughly be the same across this way and the same this way. First thing we want to find is the x component. And we're going to do that. We're going to use the equation as shown in step. This is the equation you're given. And I've substituted things in. dx is the distance along the x-axis. Remember, that's how far it traveled here in, that's how far it traveled here in meters. And we actually put that in here for our horizontal distance, and then time comes from the time we found. So we put in distance and time. We put in our knowns. We isolate the velocity on the x-axis, and we divide both by 8, and we end up with 3.4 equals velocity on the x-axis. And that's going to go, where velocity on the x-axis is also known as horizontal velocity, and so we're going to call that 3.4. And we're done with step 2. Now, if we move on to step 3, it's going to ask us to find the initial vertical velocity, or the velocity on the y-axis. And this is probably the more tricky step, and so we'll look at that. And if you look at step 3, it actually gives you 2 equations. It tells you that this is the equation for velocity final equals velocity initial plus acceleration times time. I'm showing those on the y-axis. And it also says that velocity final on the y is equal to negative velocity on the initial. And the reason for that is, if this has a y component going up, and you would have seen this when you did your PhET that introduced this idea, as it comes back down, the velocity on the y-axis is going to be exactly equal, but in opposite direction on this axis. So in this case, the value is the same, but notice they're in opposite directions. This is the velocity on the y-axis. It's worth noting that the velocity on the x-axis never changes. It would still be exactly the same. That's an important detail that you always want to remember. That never changes, but this y does. It gets smaller and smaller. If we were to draw it up here, your velocity on your x-axis would be the exact same thing, same size, but the velocity on the y-axis would actually be 0 because at its apex there. And you should have seen that when you did your simulation. But that's just explaining why this statement is true. And why this matters, we do have acceleration. That's negative 9.8. Change the color here. This is negative 9.8. And we certainly have time. That's 0.8. But we actually would end up with 2 unknowns here. And so you can't really solve an equation by itself with 2 unknowns. But what you can do is you can say, well, wait a second. I really want to know velocity initial. I don't really care about this. I'm going to take, since I know what this equals, I know these 2 guys equal each other. It's the same thing. So instead of this, I'm going to put this guy in its place. And so then we can say negative VIY equals VIY plus negative 9.8 times 0.8. Now this is something that we can certainly solve, and I'll show you that. And we're just jumping ahead here, so we can take, solve this, we would take minus velocity initial y, subtract it from this side, you end up with negative 2 velocity initial y is equal to the product of these, which is 7.84. And then to finally solve this, you divide both sides by negative 2. I'm sorry, this should have been a negative because we had a negative number there, so that would be negative 7.84. And so you're going to find that velocity initial on the y-axis is going to be equal to 3.92. And we can put that in our data table, 3.92. Oops. There it is, data table 3.92. All right, so step 4 here is asking us, now that we have the horizontal and vertical components, we can solve for that initial actual velocity of how fast I threw it in meters per second, which we're getting closer to what we wanted in miles per hour. And by the way, I just redrew this. This is essentially a sketch of the same thing that's happening here with the tennis ball. This is the motion of the tennis ball. And we have the velocity on the x component, we have the velocity on the y component. But what it's saying is, well, what is this actual velocity that we threw it at? We didn't throw it on the x, y, we threw it here. And so it gives us an equation that we can use there. It's essentially, you've got two sides of a right triangle, you're finding the third one. This is basically Pythagorean's theorem. And so the equation for there is v squared equals vx squared plus vy squared. And then if I go down here and I substitute in our vx and our vy, and then I square those and add them together, I get this. Then of course you do the square root function of both sides, and you're going to find that v equals 5.2. And so what that looks like over here is, what that's saying is the velocity here at this angle was 5.2. And this is our next thing we put in our data table is 5.2.